Okay, cool. To start. Alright, you ever get a chance to do the question that's sent? If not, please try it, because it's supposed to bring out an important point, right? So try it for yourself and see. And send, well, I send you an attempt, but still try it by yourself, and then look at the solution after, right? But I just wanted to go through some before I start. So in magnetic circuits, let me say how. So then I divide it up into different materials, and we'll give you a coil. So you have V, I going into the coil, and now based on the right hand screw, you'll basically get the flux that passes through the material, the main diameter. Cool? So that flux. When you're drawing the equivalent circuit for something in series, because you have different materials, so that there's M1, M2, M3, and M4, because each material have a different permeability, because it's different materials, the mu c will be different. And also, if you look at it, the cross-sectional area is different. So because the cross-sectional area is different, it will have a different flux density, right? So when you draw the equivalent circuit, you will have F. One resistor for RM1, then you have a next one, RM2, going through this, coming down, the next one, RM3, and you come back around, RM4. Anytime something in series, the flux, that's like current, the flux will be the same going through each material. But in each material, this one here, flux is BA, flux is BA, and the flux is BA. And same thing for this one. But since we know the flux is constant through each material, that's one thing that's changing. So the flux is the same, but also the area or the cross-sectional area is different. So if the cross-sectional area change, based on the equation, if you wanted to calculate B through each material, if you make B the subject of the formula, you will get B is equal to flux over E. So because of this, put this for M1 and M2, based on how we're looking at, if it have different cross-sectional areas, the flux density will have to change. Yeah, it will change because it depends on E. So if A change, keeping the flux constant, B will change. Right? So just knowing a series circuit, the flux is the same, which is where you all got the equation Ni is flux by R total. So you'll calculate all the reluctances and the flux will be the same. So just know when something in series, as the question has sent, the flux is the same. But when you're doing the calculation, each material have a different flux density because the areas or the cross-sectional areas were different. Yeah, so when you're doing the question, just keep that in mind. Right? Any questions on that? Okay, cool. Let me see if I get to the okay, cool. So please try the question. We'll try some. Okay, so we have two topics to run through, which is just inductance and three phase. So I'll run through those and we'll just spend some time doing some questions. Alright, so I urge you all, please stop me if I lost solid. Because if you just sit down there and listen, and you don't talk, you don't really understand, right? So you have to ask the questions to clarify the stuff that you know and the stuff that you don't know. Okay? So I urge you. So I look to start. So you went through magnetic systems and you went through the vertical lift. Make sure and go through the vertical lift with the equations and stuff. And try the tutorial 2 questions on it. So I think it's tutorial 2. I think 3 is also.
It's tutorial 3.
So try those questions for sure and know the theory behind it. So, but I look to start. Inductance isn't mostly theory, right? It don't really have much like calculations to do. Well, like he could bring a simple calculation, but there's not a big set of calculations like magnetic systems. Yeah, that's I don't know what the inductance is, what self-inductance is, mutual inductance, the dots, the coefficients, linking coefficient, and some other coupling circuits. There's mostly theory. Um, from what I remember. Done a big calculation to it. So I'll just start. Alright, cool. So the first thing we had to go through with inductance before I start anything is something called flux linkage, because that's literally the backbone of this, right? So what flux linkage is by definition is the magnetic flux. Sorry, magnetic flux is the magnetic field passing through one. So this here is a flux lines. Yeah. So the amount of these passing through the loop is basically a flux. And we know the unit is bubbles, right? So that is flux passing through, right? The thing that does make flux linkage different to flux is the amount of turns the coil have. So you could think of it as if you have the flux, the amount of turns that are wrapping around said flux is basically the flux linkage. How much of the flux linking with your coil? So the bigger coil you have, you will have more linkage. The smaller your coil, you have less linkage. That's basically it is. Flux is the amount of lines. Good. When you want to link the line, you have to make loops or turns around the flux. So fast fixed coil, the only way to change the flux linkage is to basically change the flux. So you have 2 ways to change the flux linkage. Either increase the amount of turns going around the flux, which is less practical, or just increase the flux itself, right? So that's important. So we have the equation for flux linkage, which is the amount of turns by the flux. So there are 2 ways to increase flux linkage. Increase the number of turns or just increase the flux going through or the flux of the magnetic field. Yeah. So went through all this and all right. Another thing, so the flux linkage is the total magnetic flux interact with the entire coil. Right? That's exactly what I said. So you have a magnetic flux, that's good. That's from the magnetic field. But the more turns you have, is the more linkage you have, right? So a cool way to remember it, so starting from the beginning, when you have a current in a coil, it will create a magnetic field. And that magnetic field will basically give you a flux. And the flux through the turns is what has given you the flux linkage. So if I wanted to change the flux to hence change the flux linkage, I'll just have to change the current. Yeah? Because as I continue to change the current, the flux will increase. And anytime the flux increases, you basically just have more lines cutting the turns, the same amount of turns, and you'll basically be increasing the flux linkage, right? So that's basically how flux linkage and current does work, which is important to the working of inductance and self-inductance. Current, magnetic field giving you a flux, and then the flux through the turns or the coil giving you a flux linkage, right? So that's basically what this is. Right, so talk about the equation, but we'll get into this more. But when you have flux linkage in a coil, anytime the flux linkage changes, it induces a EMF, which is basically Faraday's law. Anytime you have a change in flux linkage through a coil, it basically gonna induce a EMF. That's basically what it is. So far, anytime you change the flux linkage, you're gonna induce a EMF. And Lenz's law states that this induced EMF will oppose the change that's caused. Anytime you induce something, you'll want to prevent it from doing what it had to do. So you will oppose it, you won't aid it. Yeah. So sometimes you'll see a negative in front of here, which just basically means there's a back EMF. It was the same like a back EMF on a motor. I don't think you all did any motors as yet, but the back EMF is the same idea, right? Once you start up the motor, you have a high back EMF. Why? Because the change in flux linkage will be at its largest because it's literally now building up the magnetic field, right? So the change will be very large. And then as the core begins to saturate, it will flatline and you won't have any more change in flux linkage because the flux basically at its maximum, which is the BH curve. Alright, so as I said, if the flux linkage change, the voltage induced will change. So the faster the change, the larger the voltage, because that's how differentiation works, right? The bigger the change, the faster or the larger the induced EMF will be. Because they're trying to oppose you. So the faster you build up, the faster it will oppose you. Right? Okay, so self-inductance. So what self-inductance is a property of a coil, or basically mostly coils, right? Where a change in its own current will basically produce an EMF in itself. So yes, if exam come, define self-inductance, you need to know the definition of it, right? And well, we went through this just now. So the induced EMF in that coil, E is basically the inductance of said coil multiplied by the change in current over time, which is exactly what we did before. This is in terms of lambda, this was in terms of I, right? So the induced EMF caused by the change in flux linkage, if you keep going back, that change in EMF or the induced EMF is actually caused by the change in current, right? Okay, if the current change, the flux linkage will change. And if the flux linkage change, it will induce the EMF. Let's keep going back. So that's what this equation means. So the induced EMF is basically the inductance multiplied by the change in current. Yeah, that's what this is. And then well, we know L, this L here is not just inductance, it's self-inductance, right? Yeah. And we have two equations for inductance. We have L is lambda, which is flux linkage with respect to the currents. So flux linkage over current is inductance, which is the most important one. And then we have N phi on I, which is literally the graph, one of the graphs they have to plot. Yeah, so these are the two. But as I said, when the current is changing in the circuit, the magnetic flux link in the circuit changes, EMF is induced in the circuit due to the change in flux. If you have no change, you're not going to induce anything. Always remember that, right? So when you're writing your definitions and stuff, make sure and use the change. If you don't use change, you're going to lose marks because nothing here operates by itself. You're trying to induce something, right? So I said this already. And this just applying it over and over to drill it in here, right? Current flows, magnetic flux. If the current changes, the magnetic field changes, and a change in magnetic field induces a voltage. But this voltage is in the same coil. That's why they call it self-inductance, because you're basically inducing a voltage or EMF in yourself to prevent the changes that happen. Alright, so you'll get into more of it just now. But just remember the induced EMF is in the same coil. Yeah? So I want to, yeah, I don't want to go through it here. I'll go through it here. So let's go back to 1000. Right? So we're going back into the days. So when you have a voltage, you have a resistor, you have an inductor. So most of the time you'll have a battery and it's connected to the circuits. But you'll also have a switch. So assuming the switch is initially open, the inductor will be empty, right? So the EMF across the inductor will be zero, everything will be zero, right? The moment you close the circuit, something gonna happen. what will happen is this inductor will see the largest change in current. Remember, before the current is zero. And the moment you pull on the switch, that current going to change, the highest current change will happen. And because the highest current change happen, keep going, the highest current change will basically give you the highest flux linkage change, which will then give you the highest induced EMF. Remember that induced EMF is a back EMF. So what that back EMF means is that the voltage across this inductor will work in such a way to oppose the change that causing it. So if this is V source, this voltage across L will approximately be equal to Vs initially. So from the time it closed that switch, the inductor go and try to oppose the change that causing it. So initially at the initial state, the inductor operates as an open circuit. Yeah, and to make an open circuit, you basically just have to these two nodes have to be the same value. So if this is Vs and we've got to stop current from flowing, this have to be Vs also, which is the voltage of the node. So the moment you pull on the switch, the inductor going oppose the change that caused it. Yeah, that's basically how the initial part does work. And after a long period of time, the current will steady because it wouldn't change anymore. And the moment the current steadies or reaches its maximum value, the inductor would not see any more changes in currents. And if you go down the road, no change in currents, no change in flux linkage, which equals no induced EMF, which means that that circuit just go and see this inductor as just one straight wire, which is a short circuit. So the steady state condition for inductor is just a short circuit because it will just see it as wire. An inductor opposes changes in current. So once the current don't change after that, the inductor good. From the time you start to change the current, the inductor will step in to make sure the current change through it is the same. Okay, cool. So I got you. So flux linkage versus current. So we went through the so-far linear magnetic circuit. The flux linkage is equal to the inductance by current. So if you plot a graph with flux linkage versus current, the gradient will basically be the inductance. Alright, so this means the flux linkage is well proportional, blah blah blah, right? If current increases, right, blah blah blah, same redundancy. Alright, the induced EMF in the circuit, right, this is it. The induced EMF in the circuit is equal to the rate of change of flux linkage. So if a question comes, the induced EMF, explain the induced EMF in self-inductance, supposed to be able to run through the whole thing. Alright? Because, well, there's the main one. Notice the negative because it's a back EMF. Okay, we went through this already. So once you pull on the switch, the flux will change.
So this is where the two laws come in from yesterday.
What is it?
This is where the two laws comes in from yesterday.
The two,
Faraday's and lenses.
correct. Faraday's law states that when you have a change in flux, which is a flux linkage through a coil, it will induce an EMF, like Faraday's law. And then Lenz's law states that that induced EMF will oppose the change that caused it. That's basically how Faraday's and Lenz's laws work. Yeah? So I basically using it over more. Cool. Right. So this is an important part. So if a question comes to explain, this is basically the main parts of it, right? So the magnetic field or the process is basically linked based on four stuff, right? You have the current flow. So a current flow produces a field intensity, yeah? And that field intensity creates a flux density. So you all should remember the difference between HB flux. Make sure you know those three, right? So the flux is just the amount of lines. The intensity is basically the thickness of it. The density is the amount of flux per unit area. So just keep that in mind, right? So a current will produce a field intensity. The field intensity creates a flux density, and the flux density gives you a flux, and then the flux gives you a flux linkage. Okay? So it's I, H, B, flux, lambda. So a nice or a cool way, I don't know if it will hit. So the H is kind of the effort, like pushing water. So you're like a pump, you pushing water, right? The flux is the flow, and the lambda is the total flow seen by the whole coil. So basically, if the pipe is a long pipe, you will see a lot of flow. If it's a short pipe, you don't really gonna see much of the flow. Yeah? And well, went through this already. Same thing here, changing current, change the magnetic field, changing the flux, changing flux linkage. How do you remember that? Right? So cool. So let's get into something. I gotta ask a question here, right? I want everybody to answer. So this is a normal circuit. We have a resistor, a battery, and a switch. And we have a current versus time graph here, right? So my question to you all before we go into it. So my question to you all, you can read it if you want. The moment I pull on the switch, right? You all think the current in the circuit will instantaneously go up to the maximum value. So like you say R is 5 and the voltage is 5 volts. You'll think that the current will instantaneously go up to, in this case, it will be, I think, 1 amp. So you'll think it will go up one time to 1 amp.
No.
Alright, so you said no, okay.
Over time.
Alright, so like two people, we need two more answers.
I think it go up immediately, but I still think it wouldn't take plenty of time.
Yes, you say it go up immediately.
No, I don't think it would go up immediately, but I still think it would be in a short amount of time it would reach its
Alright,
peak.
well, those two things oxymoric, so we pick one. You think it
All
will,
right,
what
it
you
wouldn't
said?
be instantaneously.
You think it will be instantaneously?
It wouldn't be instantaneous.
Alright, Kazari, what do you think? I don't know if you're here. 5, 4, 3, 2. Right, well, that's what I here. So, yeah, so it wouldn't be instantaneous, right? Because you had to build up, remember, electrons flowing. And if something moving, it will take time, right? So, yeah, so the graph itself, it will initially start from 0, and then it will and then it will plateau. That makes sense? So that's how the graph will look, right? But this portion of the graph here, if I was to use differentiation, right? You'll think that the gradients during this portion will be the same, or would it be always changing? So if I wanted to find di over dt for this curve section, don't know if I'll remember in differentiation, y'all think the gradients will always be changing, or would it be the same for this piece?
Changing.
Changing. So that's what you're saying. Changing or always the same?
Changing.
Alright, changing, and what do you think? Changing, same.
I think the slope would be changing.
Alright, cool. Well, I'm not sure if Kazari here, but anytime you come back, hopefully here. But anyway, so yeah, so correct. You're correct, right? So the di and dt during this portion will always be changing, right? So if the di and dt always changing, anybody could answer. If the di and dt always changing, what will happen to the flux linkage? Will it stay the same, or will it also be changing?
It'll be
It
changing
would
because the
change.
current change.
And if the flux linkage also changing, what gonna happen to the induced back EMF? Would it be always increasing or always changing? Or would it stay the same?
With increase.
It will increase. Yeah? Because if we change in currents, so initially it will be the largest, right? So the question is, will it continue to increase? Will it start from a max and decrease, or would it just stay the same?
It would probably start at a max and decrease because the current would eventually reach steady state.
Alright, nice. So that's the way I think. You agree with what you said? Vernon, you agree with what Ahmad said?
Yeah.
Start at a max. Okay. So that you agree with what he said?
Yeah, I do.
Okay, cool. So you're correct, right? So yeah, it will start at a max and it will just decrease, right? Reason being, when the current reaches this point, the current are going to change. So if di and dt drop to 0, d lambda and dt drop to 0. And if d lambda and dt drop to 0, the induced EMF will basically drop to 0, which explains why at steady state the inductors are short circuit once the current don't change, right? But always remember this EMF opposes, so we know this here is basically V source, right? So if this is V source, if I do I have extra? I think I have more colors. Let's forget I have more colors here. The E will basically be this. So if this green one is E, which is the back EMF, the difference between Vs and Ve is basically, so what gonna happen? Not VL, not VL, definitely not VL, definitely not VL. Yeah, cool. So yeah, so initially let's start in here, and then obviously E now gonna go to 0. So if you subtract both of these, at this point here, when you subtract, it will basically be Vs subtract 0, which is as Vs. But initially, when you start to subtract it, it will be smaller. So you basically subtracting more and more. So Vs will basically be itself, and this you're subtracting more. So that is explaining the back EMF. So just keep going as E decreases, Vs will be, so you'll be seeing more and more Vs. Just a back EMF graph. So cool. So yeah, that was a sentence here. Initially, the change in the current with respect to time is higher, so same thing. Cool. So yeah, basically what this means is that if you know that the current through a circuit not just going to automatically go up to the instantaneous value, it will kind of explain how the build-up of flux linkage works. Yeah, so you'll get there. That basically explain. Okay, cool. Alright, so we went through this just now. So when the switch is closed, the change in current will be at its maximum. Therefore, the back EMF will be at its maximum. But this is the back EMF, right? Is the change in current with respect to time multiplied by the inductance, right? And well, we know the inductor resists changes in current due to Lenz's law, blah, blah, blah. Right, after 5 time constants, the current value will reach its maximum value, and the change in current and the induced back EMF will drop to 0, which is what you went through just now, right? In this condition, the inductor behaves as a normal strand of wire, which is basically a short circuit. So this, instead of saying a normal strand of wire, you could just say a short circuit. Yeah, same thing. Oh, cool, so nice. So we finished that is self-inductance, right? So that self-inductance was basically you inducing a flux, and you're basically going to be inducing an EMF in yourself, which is why they say self-inductance, right? So we have another type of inductance, which is basically mutual inductance, which is when if you generate a magnetic field and your magnetic field cut the coil of a next one, your flux, based on that next coil, go and induce a EMF and then a magnetic field in that coil, and then that coil magnetic field can interact with your coil, and you're just gonna keep going back and forth, right? So remember, you have a coil, that coil gonna have a current flowing through it, and hence gonna give a magnetic field. Then that magnetic field now go and cut another coil. So if you put a coil, another coil close to it, the flux of that first coil will cut the turns of this coil here. And when you have flux passing through coil, it induces a EMF. And that EMF will give you a current, and then that current will then make this coil produce its own magnetic field. Because when you have current flowing in a coil, it produces a magnetic field. And then this flux cutting this coil going to induce a EMF in this coil, and if this induces an EMF due to Lenz's law, it will be negative, right? Because it will try to oppose it. But that is the concept, all right? Mutual inductance. So mutual inductance is when a change in current, remember everything had to be changing, right? In one coil induces a voltage in another, which is Faraday's law, is all they do, right? So the change in I1 current establishes a flux phi1. So let's erase that piece so I can access it. Erase, 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 erase. Yeah, so pen, cool, yeah. So I1 produces phi1. Part of phi1 links only coil 1. So you have coil passing, so flux passing through here. So that is self-inductance part. And that is the leakage flux. Because majority of the flux you'll want it to cut the other coil, right? Not really itself. Right? And then the remaining flux links coil 2. So 1 is basically phi 1 in itself. And phi 1 2 is basically phi 1 on 2, which is the second coil. Yeah, so the total flux produced, a portion of it goes to your self-inductance, and then the rest goes into the mutual inductance of the other coil. Yeah, so basically phi total is basically phi 1, which is the inductance in itself, plus 1, 2, which is the inductance in the other coil. Alright, I'm just kind of introducing the next piece. So if I1 flows in coil 1 and produces a flux linkage in coil 2, so the naming convention is based on how you draw a circuit, right? So for this one, how they did it, lambda 2 1 is the flux linkage in coil 2 due to coil in current 1. So if they say lambda 1 2, based on what we have, we'll use this one. Right? This is just a snippet from a book I had. Right? So lambda 1 2 in this case will be flux 1 dot 2 C's. Yeah. So you have this. So lambda in our case, lambda 1 2, which is this here, would equal to M I1. And this M here is what we call mutual inductance. That's why. So that M is mutual inductance. Okay. So L is self-inductance and M is mutual inductance. Didn't really change it up first, right? So let me see. L is that equation for L. Yeah. So basically using this equation and transposing for lambda. So the same equation. So for self-inductance, it would just be lambda is Li, and for mutual inductance, this lambda will be lambda 1 dot 2 C's. And this L, this is inductance, but let's use a M, and you have to put the current that caused it. So let's see. Yeah, so that's what this means here. So if I wanted lambda 2 that 1 C, so if on this case now, it will be lambda 2 that cuts 1, it will basically be M, and the current that caused it is I2. Okay, so just use this convention, because this one from the slide. So basically, phi space space, so this one is the origin, and this one is the other coil, and this one here cutting. So if our phi, the origin is 1 and the other coil is 2, it will be the flux from 1 that's cutting 2. So I'm same thing with lambda. Lambda 2 2, it will be the flux linkage of 2 that is cutting 2. And then lambda 2 1 will be the flux linkage of 2 that's cutting 1. All the same thing. Cool. Any questions on that?
No.
So let's will see it, right? Alright, so I continue. Okay, mutual inductance. So the base here just went through the derivation to end up with this one. So we know the V or the E. V2 in this case is this voltage. And V2 will be due to the change in flux that came from 1 that cut in 2 divided by the change in time, right? Which makes sense. So that, because remember this coil here, the EMF it has is due to the flux of this V1 here. So V1 is the input voltage and V2 is the induced output voltage. It's basically a transformer, right? We know lambda is N phi. So in this case, it will be N phi 1 that cut in 2. So if you look at it, they replace this with obviously N2 phi 1 2. And then from below, you get I. Cool. And that's basically what it is. The base just went from this into the equation for mutual inductance. So this is where I remember. Which is basically the same thing we just did, which is L dV is equal to L di dt. It's really the same thing. But instead of using L, just a N. That's literally what it is. Yeah. So V2 is due to the mutual inductance caused by phi 1 on 2 by the change in current from I1 divided by dt. Because as I1 change, V2 will change, because V2 is the induced EMF. And the same way if you wanted to convert it in terms of the lambda, same way. So let's remember this is the main one. Yeah, so M, which is the mutual inductance, is equal to d lambda 1 2 by d1 2. I remember the mutual inductance works both ways, because he will also generate a magnetic field that will cut here, right? And one more thing on this slide, the mutual inductance is the same both ways, which is exactly what I said, right? So the inductance of 1 on 2 is basically the same as the mutual inductance of 2 on 1. It's the same value. Yeah, because both coils affecting each other. But the mutual inductance will be the same in both. Cool. So any questions on that?
Just remember your circuit and basically the equation.
Yes, but try to understand how the equation came. But just the process of
Yeah.
how it works. Yeah. Cool. Any more? Cool. Well, continue. So, right, the next topic is the coupling coefficients. Right? So, the linkage of flux 1 to 2 depends on the space and orientation, the axis, blah, 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 and the permeability of the medium. Okay, cool. The fraction of the total flux that links the coils is called the coefficient of coupling. So you gotta remember, right? Phi 1 is the total flux produced by this coil here. So phi 1 is the total. A portion of phi 1 goes and cuts itself, and another portion of it goes and cuts the other coil. The fraction of, so if phi 1 is the total, that's normal fractions. So if phi 1 is the denominator, so we have phi 1, 2 is the coupling coefficient. But also, when you go 1 to 2, he gonna have a magnetic field that will then cut the other coil, which is basically the same thing. So now it will basically be phi 2 is the total flux produced in the second coil, and then 2 onto 1, it will just be phi 2 that's seen at 1 over phi 2. It's just a fraction. Yeah, just know the naming conventions. Use this one. Origin and other coil. So if you see it swap anywhere, don't get confused. You know the naming convention using. So anyway, so that's basically what this talking about, right? So K, you know, K is phi 1, 2, and phi 1, cool, which is equal to, not the same. Yeah, anyway, same. So it's the main one, right? So this is the portion of 1 that cut into with respect to phi 1, which is the coupling coefficients. You have another one, so you could replace this one with n with respect to I, just this one. So n2, phi 1, 2, and I1, which is basically the same thing as going in the opposite direction. And this is the main one here. I remember we said that the mutual inductance is the same in both ways, right? And you kind of seen it with the coupling coefficients. So the total flux seen from 1 to 2 from phi 1 is basically the same thing as the flux seen from 2 to 1 on phi 2. Because the mutual inductance seen by both coils is the same. Yeah, well, eventually I will proof. And there's the big boy equation here. So that mutual inductance is equal to the coupling coefficient, which is any one of these multiplied by the square root of the self-inductances. So L1 is the self-inductance of the first coil, and L2 is the self-inductance of the second coil. M, K, same. The coupling coefficient is range from 0 to 1. So anytime you calculate and you get a value bigger than 1 or less than 0, just know you do sum wrong. Cool. Alright, any questions on the coupling coefficient?
No.
Alright, cool. Right, so the next thing is something called coupled circuits. And so this one, that's building on the same concept of mutual inductance, just in a circuit, right? So we have a system here, so you have a core, you have one coil on this side and another coil on this side. So there's V1, V2, we have an inductance and we have a resistance, which is basically an electric circuit. And we could use the right hand screw. When you use the right hand screw, you'll get the direction of the flux through the material. So we could see in here that they are opposing each other. Yeah. Normally, I1 and I2 are choosing the same direction, right? You know, like going in, going in, up, up, right? So cool. So these voltages of mutual inductance may be of either polarity depending on the size. So what I mean by that is, remember this coil will have a mutual inductance and this coil here, right? So what they basically did is that they went through and they used KVL on both coils. So you have this coil here and you have this coil here, right? So basically if you use KVL, which means that the sum of the voltages in a loop add up to 0, right? So if you do it on V1, you basically have V1 is equal to RI or R1 I1, and then you go into this. So the voltage across the inductor is L di dt, which is you're seeing it here, right? But you have one more thing, one more voltage. So you have the voltage due to R, you have the voltage due to the self-inductance, which is L di dt, but you also have the mutual inductance, which is M just like L. So it'll be M di2, because I1, the mutual inductance will be due to I2 dt. Notice the plus or minus in both of them, right? Because the mutual inductance could either aid or oppose, depending on the direction. Let's keep that in mind, right? And same thing for V2. It'll be V2 is equal to I2 R2 plus L2 di2 dt. And then we'll have plus or minus the self and the mutual inductance due to I1, which is M di1 on dt. And we know the correct signs of the mutual inductances are obtained by applying the right hand screw rule to each coil, determine the direction of the flux in the coil. We know this from magnetic systems. Right hand screw rule, you'll get the direction of the flux. Yeah? Any questions on this one? Cool.
In an exam, you'll have to draw the circuit and explain with the equations, right?
In an exam, you most likely give you the circuit and ask you to explain.
Oh, so just the equations and KVL and explain.
Yeah. Yeah. So most likely just give it to you and just ask you to explain the generation of the equation and how the mutual inductance is generated.
Okay.
So which basically just going through this. And make sure you know these equations. So, very important. And how to get them. How to get them is just using KVL on both loops. Alright, so aiding and opposing. So when it aiding, fluxes I1 and phi1 and phi2 aid one another. The signs of the voltage of the mutual inductances are the same sign as the self-inductance, right? So you'll notice that phi1 going this way up and then phi2 going this way. So you notice how they go in the same direction. So anytime we're going in the same direction, they basically aid in each other, right? So when it aid in each other, the mutual inductances will aid. So it will be plus, which is the same sign as the self-inductance, right? So same equation, but these will have the pluses. And then opposing, phi1 and 2 oppose, the signs of the mutual inductance will basically be negative because it's opposing each other, right? So left, right, problem, so it'll be negatives. So same equation, just aiding and opposing based on the direction of the flux. So basically, you need to use right-hand grip rule to know the direction of the flux and the current through the coil. Yeah. So any questions on that? Aiding and opposing for the coupled circuits?
Just one quick
No.
question
Mhm.
for your diagram. So whatever diagram would give you, and you watch and you'll determine which one if it opposing or aiding.
Yeah, so they'll basically give you material, they'll give you two coils, they will give you the currents, and they will probably just ask you are the fluxes aiding or opposing. So basically that's how they go in each flux. Do the right hand screw rule, get the direction of the flux through each coil, and just check to see if they're aiding each other or they're opposing each other. Yeah, that's right hand screw rule they're using on each coil.
Cool.
Alright, any more questions? Right, cool. So that's good? Any.
Yeah, good.
Cool.
I went through this last night, so I already understand.
Nice. So cool. So assuming, well, this is basically just writing the um same circuit you have here, but that's converting it in terms of ohmage, right? Wait, that's converting. So there's an inductor. So you have two inductors and then a resistor. So if you're just using a little bit of 1000, the inductor XL is J omega L. So not really gonna change. So if you just split it up, you express this in terms of X. From before, it will be V1 is equal to I1 R1 plus J omega L I1 because you have voltage, and then plus or minus J omega M or omega L, same thing, I2. Yeah. Question though, well, so that since you say you went through this stuff in a normal circuit, or in a normal circuit, right? You will want the fluxes to oppose each other, or you want the fluxes to aid each other. Which one do you think is the most practical?
Um, I think opposing might be better.
Yeah. Well, why? You say you're correct, but why you think opposing would be better?
Well, it will definitely be based on the current flow.
Yeah. So if you have a
The
current
current
flow,
flow of.
uh-huh.
Mhm.
Yeah, go ahead, Alison.
Yeah, so I was gonna say definitely based on the current flow of the coils because the current could enter one coil at some place, well,
Mm-hmm.
at one point, and then it enter in the other coil at the next point. It doesn't necessarily need to enter from the same point. So
True. That's true. That's true. That's true. But if the fluxes aid in each other, wouldn't it give you a larger flux in the circuit?
yeah,
Right. But if they're opposing, will they have a level of protection?
yeah.
So it's The answer to the question is it don't really have any practical. It's based on your application and what you're trying to do. Yeah. So if you see a question
Okay.
in the exam, just note it's a trick question, right? But don't bring that in exam, right? But just know it's based on the application, right? So they derived these equations based on the circuit that they had initially. Okay? So if you have a different circuit, the sign will change, okay? So if they're in series or the series A then, it will just switch to plus, right? So these will be pluses here instead of minuses.
Yeah.
Right, cool, right? Next topic, natural currents. So with natural currents, the first thing you have to do is change the circuit from DC inputs to AC inputs, right? Which is why they did this whole thing here before. They're kind of building up to the natural currents. So the new circuit will be how the J omega L1, omega L2, and you have this mutual inductance part, the minus J omega M. You all notice that this value, or this piece here, you all notice the same for both V1 and V2. It's the same thing, J omega M, same value. Let's keep that in mind, right? Which is why when they draw the circuit now, they basically have this joining each other. The J omega M, capital M, common M, same thing. Cool, so there's how natural currents happen, right? So you have two loops, but with one voltage source in one loop. So basically, you're replacing one of the sources with a AC, and the other coil is just replacing the source with a switch. Yeah, that's basically what you're doing, right? So definition, the natural direction of the currents in the loop without the source is obtained by using Lenz law, which is what we'll go through. The direction of I1 is due to the polarity of the source, which makes sense. The application the right hand screw produces, yeah, we know this already, right? Once you have the current, you could get the direction of the flux through the coil, right? So this is important here. So the natural current is basically equal to the current that flows because of an induced voltage. That basically it is. So you're just checking to see in this coil what direction the current going to flow due to the induced voltage from this one here. That basically it is. You call it the natural current, right? So it's a current that flows because of an induced voltage, not because of an external source. So you're not checking this current here, checking I2, not I1, right? So one thing you have to keep in mind, right? The terminal where the current comes out of the coil is most of the time taken as positive. Just keep that in mind, right? I'm not sure if there's anything different, but let's see. So the induced EMF in coil 2 will be in a direction such that when the switch is closed, the current flow in coil 2 will produce a flux that will oppose the main flux. Okay, so that's basically Lenz's law, right? So the moment you put this on, this coil will basically induce a voltage to oppose the change that caused it, which is basically Lenz's law, right? So let's remember the natural current is basically checking the current, the induced current in another coil by one coil with a voltage source. Hmm? Well, same thing here. The equations will change because now V2 is 0. So you end up with this circuit here. So in this circuit, with these equations, this will be the equivalent circuits. Notice I2 is basically the subject of the formula because we really care about this. It's this one here. So you have the switch. When you close the switch, you have R2, J omega 2 L2, positive to negative, positive to negative. And you'll see in that, you'll notice that the mutual opposing because opposites repel. So current flow this way. So positive to negative, good. Positive to negative, good. But this one here, problem. And this makes sense why? Because they are opposing each other. They're clearly seeing that it's opposing. Yeah. So this will be the equivalent circuits for this piece, right? So let's go back. That's basically this paragraph here. That's where you saw any circuit.
So, question, right? So, for the natural currents, we'll only be concerned about I2, not I1,
It depends on
because
which
it don't have the current source.
it depends on which
The,
coil have the AC source and which coil are the switching. So if I wanted to check the natural current for I1, I will have put the AC source on the I2 coil and put the switch on the I1 coil.
and you'll observe.
Yeah. So the equation now, V1 will be 0, and then V2 will have stay as V2. And the circle will just be, instead of I2 will be I1, this will be J omega L1, and then this one will be J omega M I2. Yeah. It just changing the subject of the formula. Yeah.
Thanks. Yeah.
Any more questions from anybody else? Or they all good? Alright, cool. Right, so next one, dot rule. So why they brought up the dot rule is because nobody like to draw core material and thing that just irritating to draw. And also the right hand screw rule, yeah, you could use it all the time, but wouldn't it just be easier just to look at a coil and you know the direction of the currents and the flux one time instead of having to draw a whole core material and all that? That basically dot rule is basically tell you the direction of the flux and current. So you're going from this big boy here. First thing you're gonna do is get the current direction, and then you basically end up with this nice circuit here, which is where I see in most transformer books. They literally draw the whole core. Right, cool, steps. We love steps. So the process with that rule, the first thing you do is you select or assume a current direction into one coil of the pair and place a dot at the terminal where the current enters the winding. So basically, initially you will know what this is, just a blank circuit. Now you won't have this. So you basically just have that, right? So the first thing you do, like we say, okay, assume I going in there. So that's the assume current. You don't know what the direction is. And then you put a dot where it enters the winding. That's the first piece. Done. Second one, you just apply the right hand screw rule to get the flux direction for your assumed current. So if you went here, obviously the flux direction will have changed up, right? So you assume I, you part that where it enter, then you use the screw rule to get the direction of the flux. Yeah. Alright, the flux produced by the current coil, the second coil must oppose. Right, so remember we have Lenz's law, right? So the flux produced by the current in the second coil must oppose the main flux according to Lenz's law, which is this one here, right? So you use right hand screw. So the first thing you do when you get the direction of the flux, then you're working backwards. So if you have this going up here, obviously, if you're trying to oppose, you expect where you need the flux to go up this way. So you're going to use that direction. So you have your right hand screw, you're basically pointing your thumb. So the thumb is the manipulating variable now. So you're basically pointing your thumb in the direction to oppose, which is up, and your fingers will basically coil in the direction that the current had to go in to oppose. Yeah? So to oppose, will basically need to go this way. Had to go out. Right? And you can't go out from the top. Because you assume the top to be the entrance, right? So basically go so, come back around and go out. So this will be I. So that's what I mean. So current dot through the entrance. After that, screw rule. Then using the screw rule in the next coil, you basically have to find the direction of the flux to oppose. From that direction with your thumb, your fingers will point in the direction of the current, and that will basically tell you the output of the current on the second coil. So that basically all this showing here, and then at the end, where they said that since the mutual inductance, right, this is what we're talking about. Since the mutual inductance voltage is positive at the terminal where the natural current leaves, the dot is placed at the terminal here. So wherever the current leaving, you put the dot. So my dot will be here. Yeah. And when you do that, you get done. So all you're gonna do is just remove the core and just draw the coil. So this coil here, it's telling you that current enter in this way. And whatever the case is, and then it's leaving in that way. And you already know the direction of the flux and everything. Yeah. So any questions on that process? Yeah, the
Could
process.
just run, man.
Yeah, no problem. So the first thing you do is you assume a current going into the coil. Let me just erase it. Mm. Right, so you want to convert this circuit into the dot rule equivalent, right? So the first thing you will do, initially you will just have a blank circuit, right? You will know any currents or anything. You will still know the flux. So you just a core with a coil and a coil on this side. That's all you have. You don't have any of these things here. So you want to convert this into the dot rule equivalent, right? So the first thing we do is assume a current enter input current. So normally the top, it don't matter which one you pick, right? It will work this way. So you could have picked this as the entrance or you could have picked this as the entrance. It don't really matter. And whichever line you put the entrance at, that is where you put in the dot. Cool so far?
Yeah.
Right, so if I put it at the bottom, this will be I and the dot will just go here. It don't matter which one you pick, either one. So we just use the top for now. I just erase the bottom. So Vernon, question, right? Based on how it is here, you could use your right hand screw and let me know the direction of the flux.
It'll be going up because of it. Your
Right,
thumb pointing up.
right. So it's pointing up. So that phi 1 to 2, right? Okay, going
Yeah.
up. So now, when you have this flux here, this flux will cut these coils here, right? And it will induce a EMF. So now, with the dot rule now, it states that you want the fluxes to oppose each other, right? So in order to oppose phi 1, 2, what direction phi 2, 1 had to go? Have to go this way or this way?
It'll go up also the clash.
Correct. Like phi 2 go into 1, right? So now you're doing the screw in the opposite direction. So now you're pointing your thumb in the direction that you know, and then you're letting your fingers figure out the direction of the current. You're using the screw rule backwards, basically. So if the thumb pointed up in the direction of flux, right? On the second coil, what direction the current's gonna be going through in the coil?
Also, now you're manipulating the thumb now
Correct. To get
to
the
find
speed.
the direction.
Yeah, so
So it could be going out.
correct. So we know it'll be going. So if it come through here, going this way, right? So you'll come out this way. Same
Yeah.
that?
And I'll
Right?
be I too.
Correct. Correct. And that'll be I2. So now, once you get that direction, you just part dots by the exit. And that's it. So now when you have it in that
So
form,
follow
yeah,
this.
go ahead.
You'll always look like this then.
Yeah, correct. And then once you have it in that form, you just remove the core. So you get us at the coil. So you end up looking like this.
I understand, thanks.
Yeah. So what this helps with is that it's no longer coupled by the core. It basically just decouple the circuit in a way. Right? So everybody good there?
Yeah.
Cool.
Yeah.
Yeah, alright, cool. Alright. So the next one is well, the voltage polarity. So that rule. So the one thing from here now, you can already tell the voltage for the mutual inductance. You can tell for the self-inductance. You can't tell what the sign will be for the mutual inductance here. So basically, you have to find a way to get a value now. Right? Okay, remember the equation, you have Ri, you have L di dt, and you have plus or minus M di opposite currents on dt. So that is the part you have to handle now. So we're reading, so the sign of the mutual inductance voltage when using coils with dots on them is determined using the following. You know that. So be listening. When both assumed currents enter or leave a pair of coupled coils at the dotted terminals, the sign of M will be the same as the sign of L, right? So I don't know if you all remember. So anytime the sign of M is the same as the sign for L, that was aiding or opposing. Which y'all better remember. So
It will be
when
opposing.
you sure? So if
Aiden,
something,
it was Aiden.
yeah, aiding, yeah. So when they aiding, it will add, right? But when it's opposing, you expect it to subtract, right? Because you're trying to oppose. Make sense? Anytime you're opposing
Oh,
something, it will be the mutual inductance will be negative. Anytime you're aiding,
oh,
you want
I
it to
thought
flip.
I was thinking like magnets. Once two of them is the
No.
same polarity, they'll clash.
Mm, yeah. Well, yeah, I understand. Yeah, that wouldn't work here. So there's just a sign for the voltage for the mutual inductance. So basically, for the dotted, you see in the circuits here, right? You have two here. I'm just put the divide, so not to confuse us, right? So in the first one, you notice that the current, remember the dot is the direction of the flux, right? So the current coming down, so it going into the dot, and same to on this side going into the dot, right? So anytime the currents coming into the dot or both leaving from the dot, the direction for the mutual will basically be the same as the L term, right? So same thing. So this one is, you can say in, and this one is out. You'll see now. And then obviously, if it going in different directions, it opposing each other, right? So I expect the M terms to be the opposite sign of L, which most of the time will be negative, right? So he going in and this side going out, he going out, this side going in. So it'll be different. Yeah. Which makes sense. If you had to look at it, if thing going in two different directions, you expect it to oppose. If we go in the same relative direction, you expect it to aid. Right. So we know this already. So if the current enters both aiding enters or leaves, and if one dot going in the opposite direction to the other one, not the dot, yeah, negative M. So currents leaving, coming into the dot, positive, same sign. Opposite, one going out, one coming in, negative. So you'll get there, right? So that's how you know the direction of the mutual inductance and the polarity field.
So this is mutual in the other one self.
Yes. All this is mutual. All this is anytime you have more than one coil, mutual. So you need to self-induct before you mutually induct. That makes sense? Because you had a L first, then mutual. So mutual is in between coils. Self is by itself. Yeah. So you kind of share in your flux in a way. Get there? So just remember the dot is the direction of the, you have the current there. But remember when you use your right hand screw, they might get a different value. So let's keep that in mind, right? So this is actually the full circuit here. So this dot rule here basically tell you, okay, I have the currents, so I know where it's going. And then these here telling the direction of the mutual inductance. So let's keep that in mind. And well, the last thing is called conductively coupled equivalent circuits. So they basically went and changed up this, well, not really this one. They used this circuit here and replaced the switch with like a normal V2 source. And they basically just derived the circuits, like where we did that one. Yeah, they basically derived this but with both sides. So why the conductively coupled equivalent circuits is just a way of replacing the magnetic coupled circuit with an equivalent circuit to make calculations, which is like KVL and KCL easier. So you all didn't do 2000 as yet. But you notice you have a space in between here. You see any space? These two coils not touching each other. They decoupled from each other, which is our problem. Because instead of using two set of KCL or KVL, I could just use one set, right? So basically what they did is in the circuit itself, these two are the same. Remember the mutual inductances will basically be the same value. Yeah? So that's basically what they did here. So they merge the two ends. You don't need to know the derivation of the circuit. You just need to mostly remember the circuit, right? So you have this side here, I1, you have R, you have J omega L1, and then you have minus J omega M. And this is the same thing for the L2 side, and you have R2, and I2, and V2. It's just this piece are just join them together. There's a merger. Yeah? So how I remember the circuit is basically just you're going up and coming around. So you go in the direction of the current. The voltages as normally match. You always start with a R1, and then you have to add the self-inductance and the mutual inductance. It's the same thing. But if you're opposing as what here, because currents going in the opposite directions, it will be a minus M, so you have minus M here. So just factorize G omega out of it. Back to the R2, and then in the middle here is always J omega M, right? So cool. Yeah, well, yeah, send the G omega branch is common, possible to replace, same thing. Cool. So any questions on this? We have to know this one though. There's a matrix circuit for it.
If you're opposing, you're saying L minus M will change.
Right, if the well right now they are opposing, right? So if you use the dot rule, the dot here, the current going this way, and here going in, right? So you know that opposing, the mutual inductance is opposing, right? So if the mutual inductance is opposing, the sign will be negative or opposite of the mutual, the self-inductance. Yeah, remember the circuit on top here. You could use, you see the dot rule there?
Yeah.
Yeah,
Yeah, the red line was blocking it. That's why.
yeah. So you see it now, so you see the currents.
Yeah.
Right, so
Now
right,
that way it could be minus.
correct, there's opposing, right? I just kind of scribble up to show you how the circuit itself, it just merge it to make an easier calculation. So instead of it being two separate circuits, it's just one. That
So
is,
if the dot was on opposite sides, then it will be plus.
yeah, yeah, they must give you the direction of the current. So you basically use the direction of the current and the dot to figure out if it's opposing or aiding.
One last question, right? Would they give you the full circuit?
Would they?
Give you the full circuit or no?
I don't know. So it'll be good to know the circuit, like know how to draw the circuit for yourself and the explanation for it. So like they might
Okay.
say, okay, what is the purpose of a why would you use or the benefits or the advantages of a conductively coupled equivalent circuits? Power. So you had to go through
You could
why.
draw it two cases.
Yeah. Well, to make the calculations easier to apply KVL and KCL. Yeah. So the magnetically coupled
Thanks.
coil with the mutual inductance are harder to analyze directly. It's hard to analyze them directly. So when you convert them to equivalent circuits, where everything is connected with wires, the mutual effects appear as dependent voltage sources. So all you're basically doing is basically going from 2 to 1, relatively. And you could use KCL, and you could use KCL really easy here. So you get this loop here, you get this loop here, and you can calculate all the values you want. Yeah. So you get there.
One last thing is sent out all the J omega M.
Correct is right. Yeah. So if it Eden, if it Eden, right? The minus m on top there, that will go to a plus m, right? So if that was
Yeah.
a plus m, the center they will have to swap. So we'll go to minus j omega m. Yeah?
Oh, I see, I see.
Just so I don't know this on top here. So since it opposing is negative, if it was a then it would basically be pluses, yeah. Yeah. Right, cool. I think that should be the last one. Right, yeah, so that was the end of inductance. So you all catch the drift of it? You all good?
Yeah, it's about.
Right, cool. So it's your thing, I'll break. You want to keep the scribbles or no scribbles?
Keep it.
Keep these scribbles, please.
Right, your thing, I'll break, and we'll go to scribbles. Okay, I got 3 minutes. Just pause here.